All right, let's do this thing. So actually, Wednesday then is like totally optional. I'll be here. I think it would make you probably do better on your final, but that's totally up to you. It will not be recorded, so, but that doesn't mean that like you don't know somebody that comes and gives you all the answers anyway. So, yeah.
Will Chapter 19 be on the test?
Chapter 19 will be on the test, and on Friday, actually, I gave out a review sheet for Chapter 19. So, and I haven't posted under doc sharing yet, but I will, or you can stop by my office and get it. Yep. I think I picked out 3 questions, maybe, for Chapter 19. Yep. All right, so we talked about different types of telescopes. This actually is a radio telescope. And as it turns out, when we're looking for intelligent life, radio telescopes are a good route to go. Now, we're actually going to start out about talking about life that's not necessarily intelligent. The video I showed you on Friday, you know, I know it seems like so long ago, but they talked a lot about just kind of your dumb life. Remember, the guy who's actually from SETI said that his colleagues, his astrobiologists, most of them are looking for that single-cell life. So when we look for life, we're talking about life on Mars. That's what we're looking for. So astrobiology actually is a field of biology and physics, okay, where basically they're looking for life or evidence that life is out there beyond the Earth, okay? So one of the things we're going to talk about, and your textbook talks about, is, as we look for life, we have to compare it to life on Earth. And how unique is Earth, okay? That's one of the things that kind of drives, well, if Earth is totally unique, then there wouldn't be life elsewhere. Okay, so as far as life on Earth, how did it come to be? We'll kind of talk a little bit about that, but one of the things that we know, we can sink our teeth into, are fossil records. And we have different sort of, things going on with regard to the Earth's crust, but if the Earth's crust is not disturbed, then basically it kind of has this sedimentary rock formation. So the lowest on sedimentary rock would be the oldest, and the top one would be the newest. So actually we look for fossil records. And all things considered, it looks like about 3.85 billion years ago, which, to put that in perspective, remember our sun turned on about 4.6 billion with a B years ago, so 3.85, that was that long to me after the sun turned on, okay, I think. So some of the earliest forms of life, and actually I think the video talked about this, when that gal was kind of walking on a beach, we think that life probably most likely arose in waters, large bodies of water first. So one of the things before life could arise on Earth was to get the hydrological cycle going, the whole water cycle going. But these are actually, I think the video talked about, they aren't the organism themselves, but they are the home that the small microorganism lived in. It kind of reminds me of like coral reef, you know, coral reef. So these have been found dating back to, you can see the caption, 3.5 billion years ago. And actually, this is a type of structure that is still formed today. I think that's pretty cool. As far as kind of the whole sedimentary rock going on, this actually is the Grand Canyon. If you were to go back to kind of the bottom of that exposed rock, you would be going back 500 million years going back in time. Now that's like 500 million, and we're talking about 3.85 billion years ago to get some of these rocks, or some of these fossils. So this is kind of neat because I don't know if you remember, we talked about when our planets were forming, when our planets in our solar system were forming. Notice there were all sorts of kind of miscellaneous stuff kind of zooming around the solar system. And so early on, actually, our moon got hit lots, the period of heavy bombardment, and all the planets got hit. And that would be a bad time for life to form. The other thing, like I said before, is we think that life started in our oceans, so we had to have oceans form. Oceans actually, life started there probably, how do I say this? But it's coming up. Some of the earliest life to form, actually, fortunate to us, were plant life that convert carbon dioxide into oxygen. the earliest Earth's atmosphere did not have oxygen. Okay, that actually came from plants doing their thing with photosynthesis. And actually your textbook says that oxygen was probably harmful, like it would kill the early organisms. That's kind of neat. Okay. Our Earth's moon, so when we're talking about planets like orbiting other stars, could life thrive or exist there? Well, we think that actually Earth's moon was a player in kind of stabilizing our Earth. It's, like this says, kind of made the Earth's kind of crazy tilted axis of rotation kind of settle down, so it wasn't like flying all over the place. The other thing, and maybe you're like me, I've heard actually the presence of the moon and the tides that come with the presence of the moon actually were important in forming life in our oceans. So when we talked about planets in our solar system, we talked about are they geologically active? And actually kind of the geological activity that the Earth's had since its beginning and up to current actually is important in life. It helps with climate control. It gives us gases, okay, our Earth tends to burp, and those gases are trapped in our atmosphere. Okay, not to mention the last one, we talked about Mars, how it doesn't have a magnetosphere, probably because it's not geologically active, most likely because it's too small and cooled down. So those are all important features. So this actually is part of a figure from your textbook. This timeline, this blue timeline, it goes, here on the left is the 4.6 billion years ago, the Earth formed. And here, with regard to present, you see so that's 4.6 billion years of forming. Now the last, this one right here, this actually is where we had plant life and animal life take off. So to me, I like this because if you just focus on how much of our Earth's existence did not have abundant life, that's how much. Okay, how much has had life? This is how much. I just think that is so cool. Okay, so now your textbook makes a thing about this. Now the theory of evolution, one of the things that I teach is chemistry. And in chemistry we talk about the atomic theory, the theory of the atom. And my husband also teaches chemistry, and he would be like, you know, no one argues atomic theory. We don't, in theory, remember, in the scientific method has undergone the initial hypothesis, experimentation, prediction, you know, it continues, and then it's elevated to a theory. So when we talk about the theory of evolution, the evidence is there, the scientists agree, okay? So you may be familiar with the theory of evolution. Actually, it has to do with, your textbook, I think, does a good job in talking about, this is a DNA strand. It's very complicated. It's all living life. Animal, plants have DNA. So what Darwin said way back when was basically, he said that there are mutations in your DNA of living creatures. If that mutation results in something positive to the species, it will be retained. It's like the survival of the fittest, okay? If that mutation results in something negative to the overall well-being of the species, that will not be retained for the next generation. Note that it's not just biological DNA mutation, but it's also behavioral traits that can be passed down from generation to generation. Okay, so we actually can use fossils to kind of see where, this is where we are today, up here at the top of the tree. Okay, over here we have animals and plants, and we have kind of bacteria and something I'm not sure what that is between. Okay, but that's where we are today, and actually that all came from common DNA. So I don't know if this necessarily goes on this slide, but the movie we watched on Friday talked about actually these thermal vents in the oceans. Okay, it's thought that not only did life begin in the oceans, but near these thermal vents you had we're going to see that in order for life to be sustained, you need to have some sort of heat source. And you need to have atoms, molecules, and you need to have liquid and water. Water in its liquid state. So this actually was back in the 1950s. They did some experiments of trying to create life, out of inanimate chemicals, and that's kind of the dude that did that. It's kind of the cool glassware he used. This green stain right here actually is a pre-cell, and so this actually was made out of inanimate material. It's not life itself, but basically it's the building blocks of life. So one of the things, and I think the video talked about this, is that as Earth has been struck by space rocks, meteorites have landed on the Earth. Comet material has actually what brought the Earth's most of Earth's water to deposit it, become bound to the Earth. That can bring with it some of this organic matter that can ultimately be used in the process of life, the DNA, RNA. So this actually kind of from left to right kind of talks about the whole biology thing. This little guy down here, oh my gosh, a tardigrade. It's about 1 millimeter, okay? And actually about 3 or 4 weeks ago, I posted it on my Facebook page because I thought it was so adorable. It is an organism that lives on Earth. But it's known to be like what we call an extremophile, meaning that actually it can exist under extreme conditions, in this case the vacuum of space. So that actually kind of goes along with the caption in the lower left there, with the fact that in the video we watched, I think kind of said this, that the terrestrial planets, let's just kind of focus on those in our solar system, the whole Mercury, Venus, Earth, and Mars, have been kind of swapping space rocks probably ever since they became kind of their own entities. They get hit, those things fly off, and they land on other planets. So it's wondered that maybe actually the building blocks, if not even life itself, actually came from another planet. So it's a thought. Is that not adorable or what? Oh my gosh. Okay. So that little bit of, remember the timeline I showed you actually is here. So the timeline I showed you with kind of the 4.6 billion years ago, up to this eon right here, okay? This eon then is actually expanded down here. So I kind of like this figure from your textbook. So if you're into dinosaurs, or if you were into dinosaurs as a kid, you might recognize some of these, the Triassic, Jurassic, and now it makes me wish I paid more attention to these. But this is actually kind of life forming here. But if you look clear over here, I mean, this little sliver here is hominids appearing. So I just think we're a blip. We're an important blip, but we are a blip. Okay. This right here is talking something from your textbook that talks about the mass of our brains. So basically the colors go like this. We have kind of purple primates, we have blue mammals, and then we have red birds here. So basically the more the dot is above the line, the more intelligent the organism. Okay, so life in our solar system. Like I said, when we look for life beyond Earth, we have to kind of focus on what is required for life on Earth. As far as we know, there are 3 criteria. We need to have some sort of matter. We need to have atoms and molecules, okay? We need to have some sort of energy to fuel life. And as far as we know, and actually this is, like I said on the slide, the biggest showstopper is we need to find a spot that actually has liquid water. The most difficult to find. So I think the textbook, I think the video we watched did a pretty good job, and your textbook, of where do we find liquid water within our solar system. Well, kind of, it's not so surprising. For years now, they've found evidence of liquid water, and I think most recently scientists are convinced that they have caught liquid water in action on Mars. Ganymede, Europa, Callisto, actually those are 4 Galilean moons that orbit Jupiter. They were the ones that had the icy crust and liquid water underneath it. Saturn's moon also has Enceladus, or one of Saturn's moons, that was the one that actually they are capturing, like if this is Enceladus, they're capturing like geysers that are coming out of Enceladus of basically liquid water that's turning to snow as it shoots out. So hey, I'm thinking Enceladus might have some relatively large creatures possibly underneath its ice sheet. We don't know. Not listed on here is Saturn's moon Titan, and the movie talked about Titan and its liquid methane. So I don't know. When we talk about life beyond Earth, why not start with our solar system? And these are some places to start. Okay, well, what about life on planets that orbit other stars? So we're seeing that most stars actually have planets, extrasolar planets. Okay, most stars actually have planets. So now, for purposes of this discussion, we're going to basically focus on surface life. Because I mentioned, for instance, Enceladus, that I really think under the icy crust of Enceladus, one of the moons that orbits Saturn, there could be something swimming around, right? Loch Ness monsters, that sort of thing. But we wouldn't be able to tell it if it was orbiting another star. So we can just have to, surface life is all we can kind of look at or hope to detect at this point, because it's hard to find the planet, let alone subsurface life on the planet. So what makes a good planet? What makes a planet possible for life, a planet orbiting another star? Well, you've probably heard of this term habitable zone. I think that is so cool. So down here in the bottom right, there are actually, the little yellow is 3 different stars, okay? And then the green actually is the habitable zone around that star. So you see Earth here actually is in the habitable zone, kind of the close part of the habitable zone. Mars is in the habitable zone of our sun. A smaller star would have a closer habitable zone, and a smaller star yet would have a closer habitable zone. So as we find planets orbiting other stars, you'll hear them talking about the habitable zone. The biggest thing about that is that at that distance, based upon the distance and the energy that the star is putting out, that is where water can exist in its liquid state. The next 3 kind of go together. They are all kind of related to the size of the planet that we might be looking for life to form on. We think that the planet needs to have be geologically active, needs to have volcanic activity, plate tectonics. The 3rd criteria up there is if it is geologically active, it should have a protective magnetic field. So those are all things that we're considering if a planet can sustain life. This must be somewhat controversial. That's kind of how the Bennett kind of in the textbook kind of describes it. But what you're looking at in this figure actually is a face-on image of a galaxy. So actually, that green area there is the stars in that part of the galaxy that's the sweet zone. That's the habitable zone of the galaxy. It's said that if you're too close to the center of a galaxy, then there's too rapid star formation, and you could like really get creamed by a hot OB type supernova event. If you're too far from the center of the galaxy, then you aren't going to have the heavy elements that you need in order for life to form and sustain itself. Another thing that maybe life on a budding planet needs is a big brother Jupiter, kind of like the Earth had a big buddy Jupiter, who actually kind of ran as a shield for incoming debris early on in Earth's history. And I kind of mentioned the moon, Earth's moon. It's a beautiful moon that created out of the Earth itself, that actually the moon was critical in life forming on the Earth. So a lot of times when you'll hear NASA say that, oh, we found these planets, a lot of times the planets are gaseous planets, just because the gaseous ones, the Jovian planets, are easier to see. But we need a terrestrial planet in order for life to form as far as we know it. Okay? So what are the likelihoods of all of this falling into place? I don't know. Well, if there is life on a planet that's orbiting another star, how are we going to know it? Now, this caught my attention. I had to read it a couple of times, and I'm not sure I really believe this. But apparently, advancements are being made in telescopes that at some point we're going to be able to actually look at a planet that orbits another star and to have the resolution to detect continents and oceans. I'm amazed by that. But probably this technology is already there. Actually, we talked about using spectroscopy to look for elements in stars. Actually, we can use a infrared spectroscopy to look for gases. Here is what the spectroscopy of Venus, Earth, and Mars would look like with regard to our atmosphere. Venus, of course, we know has a lot of carbon dioxide, sulfuric acid. Earth has carbon dioxide, ozone, water, and that bottom one is the spectra for Mars, mostly carbon dioxide, and it's kind of thin atmosphere. So there's a distinction between looking for kind of the simple life or looking for intelligent life. Okay? So, but if we find simple life, that's more than a chance that we'll find intelligent life. The difference to me between simple life and intelligent life is basically time, I think. So you've probably heard of SETI before. I think the video we watched on Friday said that SETI has been around since the 1960s. SETI stands for Search for Extraterrestrial Intelligence. So on the video on Friday, we saw the guy from the SETI Institute. Okay. Intelligent life. How are we going to know? Well, we're going to probably have to receive a signal from them. So Dr. Drake, I assume it's Dr. Drake, actually back in I want to say probably this time SETI was forming back in the 1960s, he just kind of came up with something to think about, what we call the Drake equation. And N actually, you're going to see over here, the term on the left is equal to the number of civilizations in our Milky Way galaxy that we think should be possibly making contact with us. They're intelligent and they've been around, etc. So each term in the Drake equation stands for something. Like I think I read in your textbook, it's just a kind of a means of conversation, intelligent life in the Milky Way galaxy. Now this is not the way the Drake equation looks in your textbook, but this is just one. I've seen a lot of, when I did kind of a little bit of research, I've seen a lot of Drake equations kind of take this form, where again, this is just the intelligent life in our Milky Way galaxy. The number of civilizations in our galaxy in which communication might be possible. That's what N is. And each of these terms then is a factor in whether that could be the case. So for instance, the R is what is the rate of star formation in our galaxy. The next term is the fraction of stars with planets. And again, that F sub P is kind of larger than they thought before. The N sub E is the number of planets that are habitable. The F sub L are those planets that are habitable that go ahead and support life. The F sub I is once they support life, do they go ahead and does that life evolve into intelligent life? The F sub C is does that intelligent life develop technology that actually they can communicate with other civilizations such as ours? The L term to me is the saddest. Okay, so by the time you get to the F sub C term, that you basically have a civilization that is technologically savvy, kind of like ours. The L term says what length of time is said civilization going to be releasing a detectable signal into space. It's like the longevity term. The thing that makes it so sad about the longevity term is how long is that civilization going to be alive? And once you get to be my age, you're kind of like thinking, yeah, how long is our civilization going to last? Or maybe you already think about it like that. Okay, we talked about the fact that light and all forms of electromagnetic radiations, I mean, they travel at the speed of light. So if something is 400,000 light years from us, which isn't very far, it takes 400,000 years for a signal to get to us. It takes 400,000 years for a signal to get from us to them. So are we going to be around for 400,000 years? I don't know. So those are that's called the Drake equation. And I don't have any values to plug in, but as I was researching, actually, you can plug in values and get a value for N. But it's pretty likely, I think, considering all of those terms. So SETI is search for extraterrestrial intelligence, and like I said, they use radio telescopes a lot to be looking for incoming signals. Now, the problem, honestly, is not just time, but the problem is dilution. So we said that all energies, including radio signals, actually become more and more diluted the farther from the source they are. And so, you know, it's a tough one to think that somebody could send a strong enough signal, or we could send a strong enough signal that it would survive that distance, but it's possible. So speaking of, this actually was a signal, this is a visual signal that was sent in the radio energy back in 1974. So it's a 3-minute, I don't know. It's I think a 3-minute transmission. It's weird, I guess they just sent it once, which seems weird to me. But they sent it actually to a globular cluster of stars, Messier Object 13. It's a globular cluster in Hercules constellation. Just thinking that that globular cluster, all things considered, most likely has planets that are orbiting those older stars in a habitable zone where life can have established itself and evolved to become intelligent. So that's interesting. 25,000 light years away, though. Dang. So we kind of segue into something a little bit different. How could we travel from, for instance, our solar system to another star? Well, if we want to be practical about it, we're going to have to come up with some other means of propulsion. And maybe you've heard this before. Okay. Oh, that's my next slide. So since traveling between stars, interstellar travel, unlike what Star Trek would tell you, it's kind of problematic. We do have kind of some ambassadorial sort of information leaving our solar system as we speak today. So NASA has had several missions. This actually is a figure that was part of the Pioneer missions, Pioneer 10 and Pioneer 11, that were successfully deployed and are leaving our solar system. So it's kind of like a message in the bottle. So we're hoping that maybe alien life would find this and try to put pieces together. It kind of shows you our place in the solar system. Okay. Then we had Voyager 1 and Voyager 2, and this is actually a replica of the gold record that, I think it was a record, that was placed aboard one of the Voyager missions. The cool thing about Voyager, actually, and if you go online and YouTube, you can hear the record that is in this cosmic message in a bottle. And it's just kind of neat, sounds of Earth. And it gives you instructions on aliens instructions on how to make a record player. New Horizons, which actually this summer, that was the exciting spacecraft that passed by Pluto and got some awesome pictures. I think they're still sending back images from this summer or fall. But New Horizons also has some historical stuff, again, a message in the bottle leaving the solar system. New Horizons did this thing, I don't know, maybe 6 months before, maybe a year before it got to Pluto, where it was asking people in the community if you wanted to have your name on there. And I did put our name on there. I don't know if it got on there or not. Okay, this was what I said about traveling between stars. So we're going to need some new types of technology to do that. The new types of technology I'm going to show you down here at the bottom. There's actually 3 different ways to propel your spacecraft. But if you get it to going as fast as it needs to go to make traveling between stars possible, then actually that speed is going to be problematic because it's going to make the background particles that you're running into basically like little bullets. So you're going to have to increase your speed and your shielding. Okay. But then we also have this sort of thing going on. I just think this is so cool. We talked a little bit about Einstein's theory of relativity, just a little bit, in black holes. The fact that, if you're going to fall into a black hole, basically the density associated with that black hole is so crazy that time slows so much that it looks like you kind of hover over the event horizon as seen by somebody in the spacecraft that doesn't visit the black hole. Well, this is kind of another outcome of Einstein's theory of relativity. The faster you go, time slows down. The faster you go, time slows down. So here's the deal. If you do develop the technology so you can go pushing 90% the speed of light, in your spacecraft, time is going to literally unfold more slowly. So this says basically, let's say you go 2 years there and 2 years back, okay? Well, crunching the numbers, that would be about 100 years will have elapsed on Earth. And your textbook talks about this as like a social issue. So 100 years have lapsed when you finally get back on Earth. You know, you have issues. So 3 different types of technology other than just kind of the journey, liquid hydrazine or jet fuel propellant. This one actually was proposed back in 1960, which I think is kind of cool. And it says that the fuel you could use is basically kind of I guess you would probably get the spacecraft into outer space, and then you would detonate a nuclear bomb. Okay, and then this talks about basically you can see kind of the circle on the back of the spacecraft is what they call a pusher plate. So your nuclear bomb goes off and then it pushes you. And then when you need another push, you just do it again. But Newton's laws of motion says you only have to push it once to get you between, you know, you just keep going. The other technology is a antimatter annihilation. Okay, and it was like one of the videos we said, remember the guy was shaking hands with his antimatter self, and actually it's very explosive when matter and antimatter meet. Okay, that's a thing, it's a real thing. And then the last one I think is kind of interesting. I got this figure, I got the middle figure from the internet. This is a figure from your textbook. Basically, it is a controlled nuclear fusion, and you're taking, just like our sun is taking hydrogen, fusing it together, making helium and creating energy. But you're getting the hydrogen from the interstellar space, and you're like, well, that sounds practical. But you figure there's not many hydrogen atoms to be had to put into your nuclear reactor. So basically, you need a scoop on the front end of your spacecraft to gather hydrogen that's about the size of a planet. So I think that's kind of neat. It's called the interstellar ramjet. Jamjet. Jamjet? Okay. So the last slide kind of end with all this talk of intelligent life in our Milky Way galaxy, not to mention that there are 100 billion other galaxies out there and the possibility for alien life. So I think it's quite possible. And I like what your textbook does. It kind of puts you in this scenario of just say for kicks that our civilization survives the problems it's got, okay? It will. I have no doubt if that's the case. It will develop technology to go between stars. I just know it will. It'll take baby steps. In the news recently was, and this was my point, the news recently was, well, why not go to the moon before we go to Mars? I'm like, yes, I think we should. So anyway, so I think it's quite possible that our own civilization could be traveling between stars if we survive. And then your textbook kind of describes it at, thousands or millions of years from now, we'll actually have descendants scattered throughout the Milky Way. All right? Well, think of that, and your textbook does it more details than this, but if our sun is 4.6 billion years old, and the planets that orbit the sun are that same age, there are definitely older stars than that in our Milky Way galaxy. So they have had these millions of years, that we haven't had. So to me then, I think it's quite possible that with 100 billion stars in our own galaxy, planets around most of those stars, it's quite possible that there should be life out there, civilizations that are traveling between stars, I think. So then enters Fermi's paradox. And again, I think this is in the 1960s, all these flower children thinking about this, but it's true. It's good scientific questions. A paradox just means that something doesn't quite resolve itself. So according to Fermi's paradox, if it's quite plausible that there are are other intelligent life forms that can travel between stars, okay? But the paradox comes in, but we don't have any evidence of these civilizations, okay? And so, why is that? So, your textbook, and there are probably more solutions, but your textbook comes up with 3 possibilities why that would be the case. Why there are other technologies out there, but other civilizations with the technology to travel between stars, but we're not aware of them. The first solution is that they aren't out there, okay? And the solution to that, or going along with that solution, is Earth, this particular planet around this particular star, is the only planet that could conceivably begin life and for life to evolve to ultimately have an intelligent civilization. So we are alone. The second one solution says that there are other alien civilizations out there, okay, on planets orbiting other stars, but they can't travel between stars. They can't travel willy-nilly around the galaxy. And then kind of under that, well, why can't they travel? Well, it's because traveling between stars is more difficult than you think. You know, the 3 scenarios of alternate means of propelling our spacecraft, maybe that just doesn't work, okay? The second one is they're just not curious. They're just not into it, you know. I just can't imagine that. But the third one kind of goes back to that L term, L for longevity, hopefully not for loser. Maybe actually they did develop their technology to a certain point, but actually could not develop it to ultimate fruition to travel between 2 stars because they just destroyed themselves before they got that far. And then this one actually goes back to one of the things that Stephen Hawking said in the last, maybe it's been 3 years, where he said, he basically said, Stephen Hawking said, there's most likely intelligent life out there. I don't know if he put it that way. But he said, if that life is intelligent, he said, we should start preparing now for it to be potentially hostile to us. So the third solution is that there are alien civilizations out there traveling between stars throughout our galaxy, but they have elected not to reveal themselves to us. So that's Fermi's paradox, and those are 3 possible solutions of probably a lot of solutions. You get a few beers under you, and I bet you can come up with quite a few solutions to Fermi's paradox. So, cool.